Alright, so this next section is going to cover word meaning and talking about how we store information, especially language in the brain, before we get into comprehension. So this section is going to seem a lot like memory, but it's really hard to distinguish memory from the symbol system that we use to store things in memory. So they're kind of tied together just by the nature of the fact that you can't always separate the symbols from the storage. So we're going to talk about how memory is represented through language. So a couple different memory types. We talk about episodic memories, which are like episodes, our mental diary, so the things that happen to us. Our semantic memory, which is our kind of fact-based encyclopedia of information. And then our lexicon, which is more of our dictionary, what words are and how that's tied to their meaning, which is semantics. So a super important part of this is sort of categories. Categories are a structure to memory that allow us to understand the relationship between things, which is very linguistic in nature. So a category is a group or related things, and a single concept is a member of that group. So this is sort of a constituent of a category. The way we form categories as children is sort of based on the way we perceive the world. So this gets into some linguistic determinism, that language determines thought. And it might not determine thought, but it certainly might determine categories. So our environment and the way that we structure words might influence our category formation, but we do tend to have cognitive economy. So we do like things to be simple, so we try to organize them as sufficiently as possible, and so things are linked together, not stored separately. So categories kind of fall into three basic categories. So, wow, that was cheesy, but categories fall into three kind of levels. Basic level naming is the simplest. It's the one you use to describe things in your normal day. It's the one that children learn first. It's actually a special type of category, even though it's called basic. So if you ask people what animals they have, they're going to tell you I have a dog and a cat. Superordinate is the more abstract category that those fit into. So if they ask you what animals you have, they're not likely to say mammals. And subordinate is the more specific category member. So these are categories within categories, but dogs might fall into collies and beagles because I have those two types of animals. And this is where they get more specific. So this sort of works well for especially nouns and the structure of nouns when they have that kind of ranking. So this is kind of like a biology kingdom, phylum, class idea. We're going to get more into associations and semantics. We've covered them a little already, but becoming more important now when we're talking about categories. So associations arise when words occur frequently together in text or speech, whereas semantics, they share context because they have the same features. So with association, they happen together in speech, and which makes them related, but semantics happens together because they're related to each other through the same definition, versus associations, they don't need to mean the same thing. And so that gets us into sort of classic semantic theory. So the denotation of a word is its essential meaning. So right now we're talking about all of semantics. We're kind of ignoring associations for a little bit. The connotation is all of its possible secondary meanings. So it's sort of different ways that you can use the word and mean different things than its main essential meaning. And so some theories on that, our understanding of the difference between essential meaning and connotation is referential theory. So words mean what they refer to. And that gets really tricky. It's really easy for nouns. Cats are cats. Like, that's pretty easy. But when you get into abstract concepts like justice, that concept becomes a little bit more difficult to understand. So a lot of these classic semantic theories were originally proposed based on nouns, but when we get into complex or abstract nouns and then other types of words, these theories don't work so well. Okay. And so there's also a theory of intension that is not intent, although it is very similar. It's the specification that determines how it's related in meaning to other words. So it's like how concepts are related to other concepts. Extension is what the word stands for in the world, so the thing that you can touch. And so truth theory semantics or model theoretic semantics are these like sort of logical models of complex meaning that talk about the difference between intension and extension and referential theory. Okay. Those aren't super popular because they have difficulty capturing the meanings of words and priming. So instead we're going to talk mostly about semantic network models and some sort of category exemplar models. So when we get to the very end, we'll talk about the main important points that you should have gotten. So semantic network is the idea that concepts are linked to each other because of association, because they occur together in text. So these models also capture association, but they also are linked to each other because they have the same meaning. So some phrases like peanut butter would be linked because of frequency, but not because of meaning, and vice versa. And the very first big model in this area is Collins and Quillian. And so here's a picture of what their model looks like. And so it's really based on the categorical structure, that basic level naming, which is here in the middle, the superordinate naming at the top, and the subordinate naming at the bottom. So it also tries to capture category hierarchy structure that we know exists. And then connections are ISA and HASA. So you can come back and look at this picture, but we'll talk about it here. It works really well for natural categories, like things that have that sort of structure that are arranged in this sort of biology kind of steps. And the links are ISA and HASA. So bird has wings, can fly, has feathers. So things that it does or concepts for it, but a canary is a bird and a bird is an animal. So the ISAs kind of move up and down and the HASAs are on the side, indicating features of that category. And the way they tested whether or not this model worked was using a sentence verification task. So they would ask people to respond true or false to questions like, a robin is a bird, which you would say yes, and a robin has lungs, also yes. Little awkward, but that becomes important later. Okay. So what the sentence verification task does is it shows you the response times or response latencies, which let you see how hierarchical the network is. So a robin has lungs is sort of a weird combination, which is theoretically true, but the reaction time or response time for that's going to be very slow, which implies that that is not tied to that concept so much. Some problems with that early model is that really just not all information can be represented in that structure. And it really didn't capture cojoint frequency or conjoint frequency. So how frequently words co-occur together. That's association. So it didn't separate the difference between occurring together because they have the same context and occurring together because they have the same definition. It also doesn't handle the relatedness effect. So the relatedness effect is where some statements are rejected faster than others. So a pine is a church is rejected slower than a pine is a flower. But because trees and flowers are related, they're both plants, it takes you a little bit longer to reject the second one. But that model posits that you shouldn't have that problem. It also doesn't cover the prototypicality effect, which is where we're faster for things that are more typical. Like lungs, someone saying something has lungs is not very typical, so that's why that question runs so slowly, but the model doesn't suggest that you should do that. It suggests they should all be equal. Okay. So we are much faster at a robin is a bird than a penguin is a bird. So our cute little penguin, most of the criticisms of this model were about penguins. And so we're much faster to categorize items that match in more features So the more items that have the same features, the better at it we are at saying yes faster. But the model suggested that it really should all be the same timing. And so based on these response time results, Coggins and Quillian edited their model, and actually was Coggins and Loftus spreading activation model. So similar idea, but the structure becomes much more complex, and the links between nodes, not nodes here, nodes or circles in these types of models varied in their strength. So now we're not saying that every item is equally probable, we're adding this sort of hierarchy in the nodes. Let me back up to this picture. We're adding a hierarchy here of which things were most likely because of that prototypicality effect. Right. So here's a picture of the original Coggins and Loftus model. And so things that are closer together are more related. Things that are farther apart are less related. But they're in real programming, those had numbers instead of like space. But it allowed us to add a relationship that's based on the overlap in features and an overlap in context. So both fire engine and ambulance here would likely activate red. But the idea is that if I activated car, it would slowly trickle down to all the other things that are related to car. So it would activate bus and truck and ambulance and fire engine, which would then in turn activate red, which would then in turn activate roses. So you could get from car to roses. The way to think about spreading activation is that 7 degrees of relatedness game. So this is related to this, which is related to this. That's how spreading activation works. That structure is not hierarchical, as you can tell, because the hierarchy only really works for like living objects, and it's considered a connectionist model. So things are linked together, and all those priming results that we talked about several chapters ago are based on that spreading activation, which we've been talking about as water kind of flowing downhill. So that's one set of models. Another set of models are decomposition models. Decomposition models argue that our understanding and our structure of language is really based on these sort of attributes or markers that words have. So there are semantic features for words. So bird has features of like wings and feathers and flying. And we will break down words into those features. Now these kinds of models work really well for simple domains. They do not work well for abstract or complex areas. And sometimes they're called semantic primitives. So the words are represented as combinations of the fewest features possible. So the most likely features come up, and then the rest of them just kind of get ignored. And so the big people behind this was Katz and Fodor. And the argument was that meaning can be built by combining individual word meanings. So this is really meant to explain how we understand sentences, but it's based on this idea of getting the decomposition of words. So the first thing we're going to do is semantically decompose. So we're going to break words down into their features. And then second, we're going to select words based on those constraints. So the idea is if we get to the verb like kick, we're breaking it down into its features. So kick requires some sort of object to kick. And we'll select the next words based on that constraint. So we need an object that would be kickable. So that's a decomposition theory. Some more decomposition theories. The most popular ones are feature list theory. So feature list theory is kind of like a checkbox theory. And we break things down into these lists of features that make up concepts. So features have things that are defining. They're essential. They're required for that word to be what it is. So birds have to have wings. Versus just characteristic. So characteristic features are usually true, but not always. So not all birds fly, so it is a characteristic feature, but is not defining. And the way we can test this is also the sentence verification task. So we've got two objects. So let's say a robin is a bird. And what we'll do is we'll take robin and bird and compute the feature similarity between them and see how many features they have in common. If there's a lot of overlap, we'll say yes, true, very quickly. If there's not very much overlap, if I said a robin is a fish, that is very low overlap, I would say false quickly. If it's somewhere in the middle, like an ostrich is a bird or a penguin is a bird, I'm kind of stuck because some of those features, important features, don't match. So I would have to go on to what's considered stage 2 of processing. And at stage 2, we consider only those defining features. So everything, all the characteristic ones, we are like, well, these sometimes work, sometimes don't, so I'm going to focus on only the defining ones. And that is how I can tell whether or not something's in the category, which allows me to respond to these verification tasks. The problem with this theory, its biggest crutch, is what is a defining feature? And people really don't agree on this. And so if you think about that network model, and then the Collins and Quillian models, where they basically had this sort of feature decomposition in it, where each word had is-a links or has-a links. And so, excuse me, what's happening is that we have all these features, and we could consider some features defining if they have really high probabilities and other features only characteristic with lower probabilities, but people don't really agree on these defining features, and so it's probably more likely that they're structured based on their likelihood of happening, but each person might have a slightly different set of likelihoods. And that leads us nicely into probabilistic feature models. And so probabilistic models include these like sort of essential defining features, and what we do is we look at those defining features and their likelihood of happening to identify category instances. So if I said a robin is a bird, how I would determine if that was true or false is weighted by its saliency, so how important and how big that feature is, and its likelihood of occurrence. So this model really argues that we still break down features, but then they're weighted by the likelihood of them occurring. The problem with feature models is that we can't really tell the difference between these network connectionist models and feature models. They're basically the same idea, just implemented differently. They're both economical for sure, but we can't really decide on this defining feature idea. It sounds like a good idea, but we can't really make it work. So instead, what we're going to do is, that's on the next slide, sorry. We're going to talk, one problem that we also have is this idea of interconnected features. So some features co-occur together, like wings and flying, but it doesn't really capture that relationship that features are often tied together as well. And then the biggest issue is this idea of procedural invariance. So if you ask people the same question in slightly different ways, you get different answers, but you really shouldn't based on these theories. So if I say, is a robin a bird, you're much faster to respond than to say, is a bird a robin? So instead what we're going to do is family resemblance models. So there's 3 or 4 of these, and the 2 most popular ones are prototype theory and exemplar theory. Prototype theory is this like abstract idea of a concept. So these are ideal. They don't actually have to exist in the world. You can think about this like prototype cars. And it's what people think it is like a combination of different examples of a theory. So it'll be kind of like a big mishmash of all the different dogs you've seen in your life. For a dog category. So the way we decide if something is in the category, so if I said, is a robin a bird, how would I decide if it was in the category? Is I compare the instance, robin, to my prototype for that category, bird. That's usually based on schemas, which are the ways that we sort of organize all these category knowledge. And we just compare the instance to the prototype. So it's kind of just, do they look the same? Hence the name family resemblance models. It is slightly better than feature theory. And this is where the phrase prototypicality comes into effect. So things that are typical in a prototype model are responded to faster in a sense verification task. And those features, where the features come in, is it helps fill in our schema. So schemas are like ways to do things, ways to organize knowledge. So the features help organize that knowledge. Prototype model also explains the idea of the structure of knowledge, so subordinate, superordinate, and basic level knowledge. And the argument is that we think at a basic level because that gives us economy and the most information. So it sort of gives you the most bang for your buck without too much brain power. Because basic levels are the most salient, so this sort of brings in saliency. It's how we name things, so I'm sitting in a chair sort of thing. If you ask me to describe something at a basic level, I can give you all of those features. And children seem to have special status for basic levels because they tend to learn those first in their development of language. The problem with this theory is that it still just doesn't really handle abstract concepts very well. And then there's this interesting research on other languages. So most of this research is in English, like we've talked about all year. And I cannot pronounce the name of this language, but it's an interesting language in the sense that there's a category of things that if you ask them to describe the category, members of the category include women, fire, and dangerous things. And so there's sort of this interesting interaction between culture and category representation, which is really difficult to capture in these sort of networking models. Another problem is that similarity tasks, so is this similar to this, are actually kind of circular in their logic. So this is similar to this because they share the same features, and we respond faster to these tasks because they share the same features, and it kind of is a little circular. Another example of a family resemblance theory is an instance theory. It's usually called exemplar theory. So instead of comparing our concept that we're thinking about to a prototype, we compare it to a specific example. And this is more likely the way that we work. It's the same as prototype theory, like all the rules are the same, except that we're comparing it to a specific example from memory instead of this sort of abstract ideal example. So the my GPC route's not working for that one today, but that principle is that that category includes a whole lot of detailed information about a range of instances. So it's sort of like I have a bunch of examples in this category and it contains a lot of information about all these different possible examples. That's not terribly economic, but it does appear to be the way that we structure categories. The last really set is called theory theories, which is a little annoying, but that's what they're called. And it's this idea that people represent categories as sort of little miniature theories about the world. And these theories talk about the facts of that category, so all the features for them, and how they relate to each other. And it's sort of like each category has its own little mini dictionary, so its own lexicon. And children seem to do something like this until they get a better sort of structure of their knowledge. So it might be that as we're developing language and sorting out our understanding of semantics and word meaning, is that we have these little mini theories about the world, but as things grow more abstract and more interconnected due to experience, it switches to more exemplar-based theory because I have all those experiences and I can put them together. And then models that just don't tend to work very well. Network models really do explain priming and sort of some semantic processes pretty well. So honestly, it might be that we, depending on the task, use different types of, not theories, but different types of strategies. And all of these might be available to us. It just depends on what we're asked to do or what stage of development we're in.